all things were created with immense heat and pressure, or sometimes by scientists like Ken Moody. He's a nuclear chemist whose passion is filling in the blanks at the upper reaches of the periodic table. The trick, as Ken sees it, is to be the one to name 114, which he's been on a quest to discover for more than 2 decades.
We tend to call these things discovery experiments, but we're really producing them. It's an act of creation.
Creating them with atomic colliders, quantum calculation, and something passed on to him by his mentor, Dr. Glenn Seaborg. Number 92, uranium, is the last of the naturally occurring elements. This is as far as the stars got. But Glenn Seaborg thought he could pick up where the stars left off, actually creating elements, and he did. Marching up the periodic table, creating elements 94, 95, 96, 97, 98, 101, and 102. He won a Nobel Prize for his pioneering work and created more elements than any human ever had. And then he could go no further.
Even Seaborg ran out. The process by which he was making these, he and his whole large team by this point, that way of trying to add in more protons to a nucleus, that route finally dried up. What Seaborg had been able to do, and many colleagues by this point, was sort of go step by step, add in one new nucleus at a time by just going literally baby steps.
How exactly do you take baby steps? In a science where you never see what you're working with, a lot is left to the imagination. So first, let's meet some protons. For our purposes, represented by these guys.
All positively charged. 2 positive charges repel one another.
With this repulsion, how do any of the elements stay together?
The protons feel a different sort of force as well at the same time. It's a different origin, a different type of force between them, and that's a specifically nuclear force. It's called the strong force. If they try to pull apart, it'll pull them back together. It's an attractive, coming together sort of force, but like a bungee cord, it only works over a certain distance. If you try to stretch it too far, that cord will break.
And that's where this guy comes in.
Hello.
He is a neutron.
This is a fellow who comes equipped with bungee cords like the proton.
But unlike the proton, he has no charge, no inclination to push anything away. He just sort of sits there, neutrally.
The neutron provides some remediation of the hostility of the protons, and they can survive.
Up to a point. By the time he got to element 102, with 102 protons in the nucleus, Seaborg began having problems.
Even if you add in more bungees, they might keep this cluster together here, they might keep that cluster together there, but keeping the whole big thing together, that no longer is going to work. The pushing away force starts to win.
Then in the mid-1950s, theorists presented a radical new concept of the nucleus.
There became lots of evidence to show there's a tremendous amount of very stringent, strict ordering that goes on inside the nucleus.
We're used to looking at diagrams where the nucleus is shown as a little ball with a plus sign in it, and the electrons travel in rings which are well-defined orbits. The nucleus is the same way. The protons and the neutrons can be treated as forming structures. You can think of it as rings.
And so, in fact, there are these configurations where the protons can line up in a special way in these sort of ring structures that will give a greater degree of stability to the nucleus as a whole than if there had been in some other random or messed up order. And same thing happens with the neutrons.
Just like the electrons that orbit the nucleus, the stability of the nucleus depends on how full these rings are. When you have just the right number of protons,
that is a configuration which we consider magic.
And just the right number of neutrons as well, that's called doubly magic. Theory predicts that element 114 should have this kind of doubly magic nucleus. So it should be, despite its tremendous size, incredibly stable. Seaborg would have to change his approach.
Don't add 1 particle at a time, add 20 particles at a time, add 40.
And Glenn saw this as a giant leap across a sea of instability of things that you couldn't make to an island sticking up out here.
An island of stability.
So that was what was motivating Seaborg. Could you jump this inhospitable sea to get to this, what he hoped would be a magic island, an island of stability? Way up here, where you have all the way up to 114 protons and 184 neutrons. That was the next spot, they thought, where you'd have this sort of magic stability, both a filled ring of protons and, crucially, a filled ring of neutrons.
So, how would Ken realize this dream and leap to element 114? Well, plutonium has 94 protons, calcium has 20 protons. Add them together and voila, 114. But how exactly do you add atoms together?
You can almost think of it as bowling. Each calcium ion is a bowling ball, and as the calcium approaches the target, it sees a set of plutonium pins, and there are an awful lot of gutter balls. There's that one sweet spot there. If the calcium hits the thing, you get the element 114 strike. The calcium and the plutonium fuse, and you have an element 114 that survives.
Did they make it to the island of stability? Almost, but not quite. With Seaborg gone, Moody now continues the hunt for element 114's missing neutrons.
We're 10 neutrons short of where the maximum effect should be.
And those neutrons mean everything.
Big difference. The difference between existing and not existing.
We would learn a tremendous amount of just basic nuclear physics. There's still these questions that we just can't figure out until we can make the stuff, study it, and ask these questions in the laboratory.
There are some predictions that think that it's actually a gas.
It could be a really heavy metal.
The periodic table says it should be a heavy cousin to lead and tin.
That would be very exciting, because then we could prove that periodicity is, the chemical properties continue to extrapolate as you expect from the periodic table.